the second part of today's workshop. And so it's my pleasure to introduce Serena Federico from University of Bologna. She will talk about some variable coefficients, Schrödinger operators on R times T squared. So Serena, when you want to start.
Thank you. Thank you, Santiago. And first of all, I wish to thank the organizers for the invitation to give this talk. Well, so what I'm going to present today is based on a joint work together with Giulia Staffilani, and it is indeed about some variable coefficient Schrödinger operators, not in the Euclidean setting, but on R times T2. So the plan of the talk is to give first a brief overview of classical results in the Euclidean setting and in the manifold setting. And then we will focus on the validity of Strickard's estimates and local well-posedness for two classes of variable coefficient Schrödinger operators. So the first class we are going to analyze is a class of time-degenerate Schrödinger operators on R times T2. And then if time allows, I will also discuss a class of space variable but non-degenerate Schrödinger operators in the same setting. So on R times T2, which means that the time is in R and the space domain is the torus T2, the two-dimensional torus. So let's start with some classical results in the Euclidean setting. So here, this one is the initial value problem for the Schrödinger operator with constant coefficients, the classical one. And it is well known that applying some Fourier analysis methods, one can compute explicitly the solution, and the solution is given in this form here. So the solution is essentially the sum of two contributions. The first part is the so-called homogeneous part of the solution, which corresponds indeed to the homogeneous solution of the problem. And then the second term is the inhomogeneous part of the solution, also called Duhamel's term. And here, the notation that is used, this notation here stands for the solution operator, which is written here. So essentially, this operator applied on a function of, depending on space, gives the homogeneous solution of the problem at time t, in this case, starting at time 0. So it is well known that the solution of this initial value problem enjoys some smoothing properties, and some of these properties are described by the so-called Strickard's estimates that I'm going to recall in the Euclidean setting first. In order to state the inequalities, I have to recall the definition of admissible pairs, which is given here. So n will be the space dimension, and of course it is greater or equal than 1. And then we shall call a pair of exponents qp admissible if p and q are between 2 and infinity, and if this identity is satisfied, this condition is satisfied. So by using this definition, we can now see what the Strickard's estimates say. So essentially, we have that if we consider QP and Q tilde P tilde admissible, then these two inequalities are satisfied. So the first one is the so-called homogeneous Strickard's estimate. And indeed, you can see in the inequality the homogeneous solution of the initial value problem where phi is the initial datum. And so this inequality says that if the initial datum is in L2, then the homogeneous solution belongs to this mixed space, which is LQ in time and LP in space. The second inequality is the inhomogeneous Strickard's estimate, and indeed it is about the inhomogeneous part of the solution. So if capital F is the inhomogeneous term of the equation and capital F belongs to this mixed space, then we get from this inequality that the inhomogeneous part of the solution belongs to this mixed space, LQ, LP. So essentially, if we put these estimates together, we get an integrability property for the solution U. And so depending on the regularity of our initial datum and of the inhomogeneous term of the equation, we get an integrability information about the solution U. But the reason why these estimates are so important is not only because we get information for the inhomogeneous initial value problem, but also because they allow to get local well-posedness results for semi-linear initial value problems, which means that essentially, thanks to these estimates, we can attack the problem before when capital F is of this form. Of course, P is greater than 1 and it is in a certain range, as we will see. The previous result was about the Euclidean setting, but of course, these estimates have been investigated also in the manifold setting. Here, the situation is much different because the dispersive estimate that I didn't mention, but the dispersive estimate usually fails, and the dispersive estimate in the Euclidean setting is the starting point to get the Strickard's estimates. So in this case, one has to use a different approach. The first one who obtained some and who studied Strickard's estimates on manifolds was Bourgain, who proved on the flat torus the following inequality 1. So essentially here, if you think of V0 as the initial datum, this will be the corresponding homogeneous solution. So if V0 is in HS, then the homogeneous solution belongs to L4. So here, this means that it is L4 in time and L4 in space. Notice that there is a difference between this estimate and the previous one, because in the previous estimate, we had L2 on the right-hand side, and now we have a Sobolev space. This means that we will need to require more regularity to the initial datum. And the regularity in this case depends on the dimension of the torus. So TD is, in this case, the space domain. Here, the time is in the torus, but this is just for simplicity. Actually, this estimate is true also when the time is in R. So, of course, this estimate is true also for other values of other Lebesgue spaces. So for LP with P greater or equal than 4. But here we will focus on estimate 1 for a specific reason. And the reason is the following. So when D is 2, so the space domain is the torus T2, then this estimate was proved to be sharp. And the sharpness of the Strickard's estimate is important in order to get sharp results about local well-posedness. And sharp results means that we want to ask the minimum regularity requirement to the initial datum. So if the estimate is sharp, then the local well-posedness result hopefully will be sharp as well. Before I said that this estimate is true on the flat torus, but actually this is also true on the irrational torus when D is 2. And this result was proved by Bourgain and Demeter by using the decoupling conjecture. So this is a very deep result, but this estimate is still sharp. We will refer to this estimate as the sharp L4 Strickard's estimate. And we will see that for our variable coefficient Schrödinger operator that I will present in a few minutes, we will have to try to obtain something similar if we want to obtain sharp local well-posedness result. Let me say that, of course, the problem of the validity of Strickard's estimates was considered on general compact Riemannian manifolds, and this result was proved by Bourgain, Gerard, and Tsvetkov, Tsvetkov, and they proved that on a general compact Riemannian manifold without boundary of dimension D greater or equal than 1, of course, if you consider the Laplace-Beltrami operator in the Schrödinger equation, then the following estimate is satisfied. So we have again a Strickard's estimate on general compact Riemannian manifolds without boundary. Notice that in this case, on the right-hand side, we have again a Sobolev space, but now there is no dependence on the dimension. So here, the index of the Sobolev space depends on the index of the Lebesgue space in time. So this result is really deep and really important for the reasons I mentioned before. But let me also say that this result is not always sharp, in the sense that if, for instance, you consider capital M, the manifold, to be the torus T2, then, and you apply inequality 2, what you get is this inequality here. And this is, of course, not the same as the one proved by Bourgain, because if you consider the previous estimate, the one proved by Bourgain, when D is 2, then we get that this inequality is true with HS for any S greater than 0. Instead, in this case, we have H1 over 4. So this means that the minimum regularity requirement for V0 has to be H1 over 4. So it has to stay in a Sobolev space, which is at least H1 over 4. However, estimate 2 is sharp, for instance, on the sphere S2, and this is due to some nice global geometric properties of the manifold. But how do we use essentially Strickard's estimates to prove local well-posedness for semi-linear initial value problems? In this case, on manifolds, of course. So here there is a very brief scheme of how to use these estimates. And essentially, the first step is indeed to prove the Strickard's estimates in mixed Lebesgue spaces in general. And then one tries to use these estimates to prove Strickard's and multilinear estimates in Bourgain spaces. Bourgain spaces will be introduced in the next slides, essentially, in the next few slides. So at the moment, just consider that this will be a key tool in order to prove our result. So this is the second step. So once one has Strickard's and multilinear estimates in Bourgain spaces, then one can apply a contraction argument in Bourgain spaces to prove existence and uniqueness of the solution and also regularity properties for the solution. So one uses the contraction argument in Bourgain spaces. Let's finally start with the first class of variable coefficient Schrödinger operators that we will consider. This class will be indeed on R times T2, and the class is denoted by LG. So we will consider operators of this form, IDT plus G prime of T times the Laplacian. So here G prime is a C1 function, and G is such that it vanishes at 0, and also the first order derivative of G vanishes at 0. And additionally, we require that G is strictly monotone, and we will see why we need this condition here about the monotonicity of G. This class of operators is a class of time-degenerate Schrödinger operators because of the requirement on G. So we require that G prime vanishes at 0. So this introduces a degeneracy in the equation. So let me also say that this class of equations was considered in the Euclidean setting before. So the first paper where, as far as I know, where the study of this class in the Euclidean setting appeared was in a paper by Cicognani and Reisig, who considered this class of operators in the Euclidean setting in the case when G prime is T to the power alpha. And they considered the problem of the local well-posedness of the linear initial value problem. And they solved the problem both in Sobolev and Gevrey spaces. Then still in the same case, when G prime is T to the power alpha, Giuliano Staffilani and myself, we proved the validity of local smoothing estimates. And thanks to this estimate, we could obtain some local well-posedness results for the nonlinear initial value problem, even with derivative nonlinearities. And also, Michael Rozhansky and myself, we considered a class, still in the Euclidean setting, a class like this one, but more general in a sense, because we can assume G prime to be more general. Let's say we don't assume G to be strictly monotone. And so for this class of operators in the Euclidean setting, we proved Strickard's estimates, but also homogeneous Strickard's estimates. So as I said before, the key tool to analyze the problem of the local well-posedness of the semilinear initial value problem in the manifold setting is given by the use of Bourgain spaces. So let me recall what the spaces are in the case when we consider the Schrödinger operator with constant coefficients. So when G prime equals to 1. So when G prime is 1, so essentially this means that G of T is T, then these spaces are defined as follows. One considers the space capital X of functions defined on R times the torus TD in general. And the space X contains these functions, which are the functions which are Schwarz in time and smooth in space. And then for S and B in R, the space XSB is defined as the completion of X with respect to this norm here. So in this norm, you can see the Sobolev weight, because now the space domain is the torus, so the dual variable is now lives in Z to the power D, so we use the notation K. And so this is the Sobolev weight. But here we have an additional weight. So this is to the power 2s, and this is the index s. But the index b is used to identify the power of this additional weight, which is the so-called dispersive weight. Notice that tau plus the modulus of k to the power 2, in the case when g prime is 1, is nothing else than the symbol of the Schrödinger operator. So this space is connected to the solutions of Schrödinger equations. And why it is like that? Essentially, consider the homogeneous Schrödinger equation, and suppose that U is a solution of this homogeneous equation. Then if you apply the space-time Fourier transform, you get this equation. This means that if U is a solution of the homogeneous equation, then the space-time Fourier transform of U is a solution of this equation, which means essentially that the space-time Fourier transform of the solution is supported in this set. And this essentially shows that the solution, the homogeneous solution belongs to Bourgain spaces, but actually also solutions to the semi-linear initial value problem belong locally in time to these Bourgain spaces. So which means that a cutoff function multiplied by U still belongs to the Bourgain space XSB. Of course, the space XSB one uses depends on the equation one is considering. So in this case, in the definition of the Bourgain space, we have, of course, the dispersive weight, which contains the symbol of the operator. So if you consider another operator, let's say, for instance, the KdV equation, then you will have to consider a different kind of dispersive weight in this definition. So essentially, the kind of Bourgain space we use is strictly related to the equation under consideration. And indeed, in our case, we cannot use the Bourgain space, which is suitable to the constant coefficient operator. So we have to define and we have to find a new suitable Bourgain space, which works with our time-degenerate equations. And in order to do that, we had to define a suitable substitute of the standard Fourier transform in time. And we decided to call this new Fourier transform subordinate to a function g. So this is how it is defined. We pick a function g, which is smooth, and it is such that g vanishes at 0 and g is strictly monotone. Then we define the Fourier transform and the inverse Fourier transform subordinate to g as follows. So this one is the Fourier transform subordinate to g. So the difference with respect to the standard one is that here we have g of t in place of t. But for the inverse Fourier transform, we have in the integral, again, instead of t, we have g of t, but we also have this additional function. So we have g prime of t that multiplies the integral. And I will say why we need this g prime in the formula. So in the sequel, we shall use the notation u tilde tau for this new Fourier transform. So for the Fourier transform subordinate to the function g. The reason why we have this multiplication by g prime in the inverse Fourier transform is in order to have this property, which is the property one expects. Namely, we have that the function u coincides with the inverse transform of the transform of u. So of course, one wants to have this property. A second key property that we will be using in our analysis is this one. So essentially, if we apply the Fourier transform subordinate to g to the derivative in time of u, we get a property which is similar to the one of the standard Fourier transform. So we have a multiplication by this monomial, and then we have the new transform, but now not applied on u, but applied on g prime u. So this is a difference with respect to the classical case, but this is enough for our analysis. Let me also stress that if you consider, for instance, a higher order derivative in time of the function u, you don't get exactly this formula here, but you get something more complicated. But essentially, we don't care right now because for us, it's enough to have this property here, the second property. And the other properties are essentially a sort of analog of Plancherel theorem. Of course, it's not exactly the same, but we have again some relations between the norm of the new transform in L2 and the norm of the function. So when no confusion arises, we will use this notation here, U tilde of tau k, for this new space-time transform, which is essentially the standard Fourier transform in space and the new Fourier transform in time. So this is the Fourier transform subordinate to G. By using this new Fourier transform in time, we can now introduce some Bourgain spaces, which are suitable to our analysis, which are called XSBG and X tilde SBG spaces. So the difference with respect to the previous space, the classical one, is that essentially we still consider the previous space capital X, but now we consider the completion with respect to a similar norm. I say similar because here we have to consider this new space-time transform. So we don't have the classical space-time Fourier transform, but now in time we use the Fourier transform subordinate to G. And then once we define this space XSBG, we define also the space, the tilde version of the space, which is the space of functions belonging to XSBG, and such that G prime U also belongs to the same space. So the norm in this space is essentially similar to the previous one, but now here we have to consider the new space-time transform of the function G prime times U, not only on U as in this case. But why should these spaces be good for our analysis? So again, let's try to understand why by looking at the homogeneous equation for our operator LG. So if we consider the homogeneous equation, which is this one now, and we assume that U is a solution of this equation, then if we apply this new space-time Fourier transform, so and in time we use the new Fourier transform subordinate to G, where G is essentially the function appearing here, then if we apply this transform, we get that if U solves this equation, then the new space-time Fourier transform of G prime U has to satisfy this equation, which means that this function here is supported again in this paraboloid. So again, we have a similar property. And moreover, if we consider G prime to be 1, so we go back to the constant coefficients case, we get exactly the classical definitions and the classical properties, namely the properties holding for the constant coefficient case. We also had to use other spaces in our analysis, but I won't go into the details, and I will go back to these definitions in case it's needed later during the presentation. Let's focus now on the initial value problem for our operator LG. So thanks to the form of our operator LG, which is this one, we can again solve explicitly this initial value problem, and we get again that the solution is a sum of two terms. The first one is the homogeneous part of the solution, and the second one is Duhamel's term. So now this capital STS is the so-called solution operator, and now the definition of this operator is this one here. Recall that now we are on the torus. Here the formula is written for the torus TD because this holds in TD, but then we will specify our analysis in the case when D is 2. So notice that in this definition, we have G of T minus G of S. And indeed, when G prime is 1, namely G of T is T, this is exactly the solution operator in the case for the constant coefficient Schrödinger operator. And this solution operator still enjoys some nice properties that are needed in the analysis, which are listed here essentially. So our goal now is to consider this initial value problem when capital F is of this form. So G prime of T times the modulus of U to the power 2 times U. So we want to analyze a cubic NLS. And notice that here we still have G prime in the nonlinear term. But actually, we can also consider the problem when F is slightly more general. But just to simplify the explanation, I will focus on this case now. And the goal is actually to prove a sharp local well-posedness result. Namely, we want to prove that the previous initial value problem with capital F of this form is locally well-posed in HS for S greater than 0, which is what one has in the constant coefficients case. So what's the scheme now that we have to follow? So if we go back to the scheme that we saw in the introduction, right now we are considering the problem on the torus R times T2. And the reason why we focus on T2 is because we know that the L4 Strickard's estimate proved by Bourgain is sharp and it gives sharp results. So what we want is to prove a sharp Strickard's estimate in L4 also in this case. And of course, the estimate will be slightly different because we have variable coefficients. Then again, we want to use this estimate to get Strickard's and multilinear estimates in our Bourgain spaces, which are the XSBG spaces or X tilde SBG spaces. And finally, we want to use these results, these estimates, to prove a contraction argument in the Bourgain spaces in order to get local well-posedness results and also properties for the solution. So let me say then which kind of estimates we proved for LG and also which kind of connected results we obtained. So the first property, let me call it property. These are a series of results which are proved, but now I want to call them properties essentially. And okay, so the first property is the following. We consider a function phi capital N, which is in L2 of T2. So it depends just on space, which is such that the Fourier transform is supported in a ball of radius capital N. So now we are considering this kind of balls because recall that the frequency variable now belongs to Z to the power 2. And then what we proved is the following for such functions. We proved the following localized Strickard's estimate, frequency localized Strickard's estimate, which means that it is a Strickard's estimate for functions having a frequency localized Fourier transform. So in this case, we have an L4 Lebesgue space on the left-hand side. On the right-hand side, we have L2, but we also have n to the power epsilon. And on the left-hand side, in the Lebesgue norm, we also have a weight which depends on our variable coefficients. And essentially, thanks to this estimate, which is the frequency localized estimate, we can get the Strickard's estimate for general functions. Sorry, here there is a typo. There is no phi n, but this is phi. So when we pass from the frequency localized estimate to the general estimate, here we get an H epsilon Sobolev space for any epsilon greater than 0. And this epsilon is a consequence of this n to the power epsilon on the right-hand side of the previous inequality. Actually, the second property is a generalization of this, is a refinement of estimate 3. So let me skip this. But let's focus on the third property, which holds true for general functions. So notice that in here, we used homogeneous solutions. So we used functions of this form, S of t applied on phi n. Now in property 3, we get an estimate for a function defined on I times t2, where I is a finite interval of time. So if we consider a function un now, such that the Fourier transform is again supported in a ball, then for S1 and B1 in certain ranges, we have that this inequality is satisfied. So notice that again, on the left-hand side, we have a weighted Lebesgue norm, because here we have G prime to the power T to the power 1/4 times UN. And so the coefficients of, in our operator LG appear in the estimate as a weight. And on the right-hand side, we see the appearance of Bourgain spaces. So if we pass from the localized version of this estimate to the general estimate, essentially what we get is that this estimate is satisfied with the Bourgain space XS1B1G without any localization. So essentially, to pass from the localized estimate to the general estimate, one uses literal Paley decomposition, and then one applies the localized estimate, and one can get the result for the function, for the starting function. So by using the previous properties, we finally get some XSBG Strickard's estimate and also some trilinear estimates which are needed in order to prove local well-posed results. So the Strickard's estimates in XSBG spaces are the following. So we assume that I prime, which is essentially the image under G of the time, the interval of time capital I, equals to delta. So this gives a sort of size of the interval of time. Then we have the following homogeneous Strickard's estimate and this inhomogeneous Strickard's estimate. So the first one is a sort of homogeneous Strickard's estimate in the Bourgain space XSBG, because on the left-hand side, we have the homogeneous solution. Here we have a weight which depends on the coefficients in our operator. And on the right-hand side, we have the initial datum. So you can think of this as a sort of Strickard's estimate in Bourgain spaces, the homogeneous version. Similarly, this one can be thought of as the inhomogeneous Strickard's estimate in XSBG spaces. So here we have G prime W, here we have G prime W, that is, this is like the inhomogeneous term of the equation. So this will be the inhomogeneous part of the solution. And here we have the weight, which again depends on the coefficients in our variable coefficient Schrödinger operator. So these two are the Strickard's estimates. And then this one is the trilinear estimate that allows to solve the semilinear initial value problem, the cubic one, because this estimate allows to get an inequality for a Bourgain norm of the nonlinearity. And so we can estimate this Bourgain norm as a product of Bourgain norms. And notice that here we have XS B prime will be smaller than B, and we will have to estimate this term by using this additional inequality. This is important in order to close our contraction argument, as we shall see in the next slides. So now that we finally have estimates in Bourgain spaces, we can solve the semilinear initial value problem. So the result that we proved is the following. Let S be greater than 0 and B between 1/2 and 1. Then for every U naught in HS, there exists a unique solution of this initial value problem. So we have a cubic nonlinearity, and we have also G prime. So we have a unique solution in the time interval minus t, where t is a suitable finite time depending on the Sobolev norm of U naught. And the solution not only belongs to this space, but locally in time, it also belongs to this Bourgain space. So let me briefly give you a sketch of the proof in order also to show where the Strickard's estimates come into play. So the proof is based on the standard contraction argument. So the first step is to define a space capital X, which in our case is defined this way. So it's defined this way because essentially we have estimates in Bourgain spaces. So the norm that we have to use is the Strickard's norm, namely the norm that appears in the Strickard's estimates. Then the second step is to define a suitable map, which is this one, which remains the form of the solution. And what we want to prove is that this map is a contraction. So we can apply fixed point theorem and get that there is a unique fixed point. So we have a unique solution, and the solution will belong to the suitable space. So the goal is to prove that this map is a contraction. And we want to prove that this map is a contraction on a certain ball in capital X. So the ball BR is essentially the set of those functions having this Bourgain norm bounded by R. and R will be given in terms of the Sobolev norm of the initial datum. So to prove that essentially phi, the map, sends the bold BR into itself, which is the first step to prove that phi is a contraction, we essentially have to prove that this norm, this Bourgain norm, is bounded by R. And so if we write down what this norm is, it is nothing else than this. And then we essentially write down explicitly what the map is, and we get that this norm is the sum of these two pieces. And we want to prove that the sum of these two pieces is bounded by R. But in order to do that, we simply apply the Strickard's estimates. So we want to bound these two. So on the first one, we apply the homogeneous Strickard's estimate. On the second one, we apply the homogeneous Strickard's estimate and then also the trilinear estimate, and we get this product. Then we apply the last estimate that we saw on this term where B prime appears with B prime smaller than B, and then we get this inequality here. So recall that R depends on the norm of U naught, and so essentially this sum is bounded by this sum. And then since these exponents are positive, we can choose delta sufficiently small in order to have that actually this quantity is bounded by R. And so this proves that phi sends BR into itself. And then the second step is to prove that actually the map phi is a contraction, but this essentially follows the same lines. So essentially what one has to prove that phi of V minus phi of U in the suitable norm is bounded by the difference of the norms of the functions. And this is doable simply by writing this difference in this way and applying trilinear estimates, some trilinear estimates which are slightly more general of the previous one, but of the same form. So I won't go into the details, but essentially the key part is the very first one. And also the second part, of course, uses Strickard's estimates and trilinear estimates. So this finally concludes the proof and shows that there is a unique solution, and the solution also belongs locally in time in our Bourgain space because of the definition of our space X. So I won't go into the detail of this case, but essentially if we consider a nonlinear term of this form where F vanishes of the same order as G prime, then by using some more general estimates, which are listed here, one can conclude the same result. So I won't go into the detail of this. So unfortunately, I don't have much time to discuss this, this class of space variable coefficients operators, but let me just quickly say that in this case, we have a non-degenerate operator, and here the coefficients are strictly positive. So here we have an elliptic operator instead of the Laplacian. And for this class, we don't prove Strickard's estimate, but we manage to use the Strickard's estimate proved by Bourgain and to conclude a sharp local well-Poisson result for the cubic NLS associated with this variable coefficient Schrödinger operator. So I want to conclude just with some remarks. Sorry for scrolling. So what I want to say is that the strategy that we use to prove local well-Poissonness in HS for s greater than 0 for the cubic semilinear initial value problem is, of course, the same and can be easily adapted to prove the corresponding local well-Poissonness result for the quintic semilinear initial value problem on R times T2, on R times T, so for the one-dimensional torus. And actually, the results holding for the class LG, which are proved on R times T2, can be generalized into the setting where we work on R times TD by using a combination of our strategy with known results. For instance, by combining our strategy with the result by Burke, Gerard, and Svetkov. So this can be done very easily. So it should still work that the same results hold true in the higher dimensional setting and on general compact Riemannian manifolds. So I think I finished my time. So thank you very much for your attention.
Okay, thank you very much, Serena, for such a nice talk. Now, someone want to ask any question, please go ahead. Mute yourself and ask. We have bullies.
Yeah, there is a question in the chat.
Yeah, bullies is asking, question 1, why nonlinearity? Why nonlinearity has GT? I don't understand. What nonlinearity has GT maybe?
Yeah, so I can explain this. Yeah, so the nonlinearity has G prime. Let me go back to the form of the equation. Yes. Here we have G prime, and the presence of G prime is essentially dictated by our Strickers estimates, because the Strickers estimates that we have, both in Bourgain spaces, but also in Bourgain spaces, is if you see in the nonlinear, let's say in the inhomogeneous Strickers estimate, you have a weight here, which is G prime, but you also have a weight inside the integral, which means that the kind of nonlinearities that we can use necessitate of the presence of G prime. And that's why you see the appearance of G prime also in the nonlinear term. This is dictated by the Strickers estimate that we have essentially. Yeah. So one can do something slightly better in the sense that one can, instead of G prime of t, as I was mentioning, one can use a function f of t, which is not exactly G prime, but again, f of t has to vanish of the same order as G prime. Okay, what if I have coefficient with respect to time and space? Okay, so this is, okay, if we have coefficients in time, let's say we have G prime, and we have the same structure as in the space variable coefficients case, let's say like this. So if we have I dt plus G prime of t a1 of x1 dx1 squared plus G prime of t, a2 of x2, dx2 squared, one can prove again local well-posed results again in as before. So one can use a combination of this. But if you have a general coefficient, let's say a of tx times the Laplacian, let's say even on r, let's say I dt plus this on r times t2, I don't know. It's very complicated, but the problem is given by x, not really by t, but the space variable gives a lot of problems. So, and that's why in this case we have a specific structure. The structure of the operator helps a lot. And if one consider a very general structure, let's say a very general elliptic operator, it is not clear how to deal with the problem. Thanks to you, Bolis.
Maybe any other questions?
I have one question, Serena.
Yeah.
Maybe could you mention something about the membership of the parameter B to the open interval half one? If one can go, if B can be outside of this interval?
Can you repeat the question? So,
could you mention some detail about the membership of the parameter B to the open interval 1/2 1?
Yeah. Okay, yes. Well, so this is important. The reason why this happens is because, okay, one can prove that actually one has some estimates for some values of B. So B has to be has to be in this range because, okay, this is a technical condition, and this comes from, if I remember well, it comes from some duality arguments. For instance, let me see, maybe I can say something. Okay, it comes essentially, it is a condition that somehow is connected with this inequality. And so what one has is that since these arguments are proved by duality, one gets some ranges. It's a technical condition. So it's essentially connected to this. So one has some some conditions. You want S1 to be positive, and then you get also some conditions on B1 and on B. So yeah, it's a technical condition. Yeah.
Thank you.
Bolis also asked, what about global well-posedness?
Okay, about global well-posedness, I haven't studied this problem, but I think it is true. I mean, at least in the case for LG, I think that by using classical results, again, following the same lines, one should be able to prove that global well-posedness is again true. This is true on the torus. So on the torus T2, when G prime is 1, so with classical coefficient, constant coefficients, one has global well-posedness. And I think it should hold also in this case, but I have no result. I mean, I haven't studied this problem.
Okay.
Yeah.
I don't know, maybe any other question?
Yeah, so with this G variation, like this G modified Fourier transform, did you ever try, or does it make sense to study other dispersive equations like KdV or wave?
Yeah, I mean, if you use that's a good question. Yeah, if you use the same strategy, exactly the same, and you define accordingly the Newburgh spaces, you get the same results. So yeah, I'm sure about that one can do the same, because the time is somehow separated from the space, and the space is the one, the space variable is the one that gives much problems. So yeah, one can again use the same strategy for KdV or other dispersive equations. Yeah.
Thanks.
You're welcome.
I have a follow-up question, Serena, because the analysis is in the two-dimensional torus, that about the torus of higher dimensions.
One can apply again the same. Okay. So, for instance, sorry for scrolling again, but for indeed this was my final remark, because we decided to consider the case when d equals to 2, because this is sharp. So one can get the sharp result, let's say. So you ask V naught to have the minimum regularity requirement. If you use TD, you can use essentially this estimate, in the sense that you can find the corresponding estimate with the weight here. Let's say you will find the weighted version of this. You will have something like G prime. And then from this estimate, again, you can find the estimates in Newburgh spaces and so on, and find the corresponding result. Of course, you won't have a sharp result, but you will have corresponding results. So yes, it works exactly the same. And the same can be done, and instead of the torus, one can use a general manifold like in this case, and then you will most probably find something like G prime of T, and then you iterate the process. I mean, one combines what is well known and our strategy with our Newburgh spaces, and one finds again the results holding in the constant coefficients case.
Okay, thank you.
You're welcome. Of course, here G prime will be to the power 1 over P. Essentially, there is a certain power which depends on the Lebesgue space, but essentially, yeah, that's the idea.
But in a general Riemannian manifold, how you use the Fourier transform, or do you use another technique? In
the general compact Riemannian manifolds, you use the suitable replacement of the Fourier transform. So you use the spectral decomposition. And
of the Laplacian, you mean?
Yeah, and that's the reason why essentially this is done for the Laplace-Beltrami operator. So they use the spectral analysis, the spectral decomposition, and they perform the analysis by using this tool.
But then how will be your Fourier transform taking into account the time? How you take the spectrum of the combined operator or something?
The time is always real, so it's always in R. So it's just the space that is in the manifold. So the time Fourier transform is the Euclidean one, also in the manifold setting, and here it will be again the new Euclidean one. So let's say the subordinate to G version.
Okay. Thank you. I don't know if maybe there is more questions. If not, well, thank you very much again, Serena, for your nice talk.
Thanks to you, and thanks for all the questions.